So we just looked at a question where we were finding the absolute extrema of a continuous function on a closed interval. And we found that we could use something called the candidate test to very quickly and easily find those absolute extrema. In this second example, we're asked to find the locations of all extrema for the function f at x equals 6 times the cube root of x plus 3x to the 4/3. And then we're asked to sketch a graph of this function. Notice, however, that in this case we do not have a closed interval, and therefore the candidate test is not available to us. And so we need to use another approach, and we're going to look at that now. Again, just like the last time, the first thing we want to do is take the derivative, and this is a very straightforward derivative. F prime at x is going to be 1/3 times 6, which is 2x to the minus 2/3, plus, and we've got 3 times 4/3, which is going to be 4x to the 1/3. As was the case in the last example, I'm going to find this more convenient if I don't have these negative exponents and these rational exponents. So I'm going to rewrite this as 2 divided by the cube root of x squared plus 4 times the cube root of x. Now I'm going to try and find my critical values, and so I have to take this derivative and set it equal to 0, and then later I'm going to look for where the derivative fails to exist. In order for this to equal 0, I'm going to pass the 4 cube root of x over to the other side of the equation, and I'm going to be left with 2 over the cube root of x squared equaling negative 4 times the cube root of x. And then just like the last time, good things are going to happen. I'm going to multiply this denominator on both sides of the expression, and I'm going to be left with 2 equals, and I got negative 4, and the cube root of x times the cube root of x squared is the cube root of x cubed, which is just x, leaving me with x equals minus 1/2. I'm going to now go over and try and see where this function fails to exist, where this derivative function fails to exist. And I see that the only place I have to worry about is my division by 0 when x equals 0. And so I have two critical values, one at x equals minus 1/2 and one at x equals 0. Now what I want to do is I want to create a labeled sign chart to help me to analyze what's going on at these two places. So I'm going to have a couple of horizontal bars here, and I'm going to have 2 vertical bars, one for each critical value. It's important that I remember to label my sign chart, and so this is x equals minus 1/2, this is x equals 0, and I'm interested in looking at f prime and then at f. To the left of minus 1/2, and I'm going to go back and look up here at my derivative function. To the left of minus 1/2, I might be inclined to try maybe try negative 1 as a value. So if I put a negative 1 into here, it becomes positive 1. So this is going to be 2 divided by the cube root of 1, which is 2. And the cube root of negative 1 is negative 1, so that's going to be minus 4. So I get 2 minus 4, which is a negative number, which tells me that f is decreasing. Between minus 1/2 and 0, I have to be a little bit more clever, but I might try something like minus 1/8. And if I took minus 1/8 squared, that's going to be 1 over 64, and the cube root of 1 over 64 is 1 over 4. So I get 2 over a quarter, which is 8. And here I'm going to get the cube root of minus 1/8, which is minus 1/2. And 4 times minus 1/2 is minus 2. So I get 8 minus 2. So I have a positive number here, which tells me that the function is increasing. To the right of 0, I might choose 1. And I can see it doesn't really matter what I choose because this is going to be positive and this is going to be positive, which indicates that this is positive. So I'm going up. It's probably a smart idea for me to think a little bit about what's going on these two vertical bars. X equals minus 1/2 was what I got over here when f prime equals 0. So I've got a horizontal tangent there. And that tells me right now it's going down, leveling out, and then going up, which gives me a local minimum. Possibly an absolute minimum, we're not sure yet, but at least a local minimum. Here, remember, at x equals 0, the derivative failed to exist. So I have to think a little bit about what's going on. Why would the derivative fail to exist? Well, the derivative fails to exist because when I put in a 0 here, I have a division by 0, which means the derivative is going to infinity. It doesn't get to, we're not allowed to have x equals 0, but as we approach 0 from either side, the derivative is going to infinity. So that makes me think that I've got either a vertical tangent or a vertical asymptote. If it was a cusp, the infinities would have to be different. I'd have to be going from minus infinity to plus infinity. The function would have to be changing from increasing to decreasing or decreasing to increasing. So I know I've got either a vertical tangent or a vertical asymptote. But if I go back and look at the original function, I see that the original function is continuous at 0. If I put in 0 here, I get 2 times 0 plus 4 times 0 is 0. So f at 0, sorry, up here, f at 0 is 0. And so the function is continuous, and that means it can't be a vertical asymptote. So here, I have a vertical tangent. I don't really need that in order to find the extrema, but because I'm asked to graph this function, it's going to be helpful for me to know that. So now I know that we have we have a local minimum here. And by looking at the labeled sign chart, I can see that the function is decreasing everywhere to the left of this local minimum and increasing everywhere to the right. So that tells me that not only is this a local minimum, this is in fact an absolute minimum. Even if we go off to positive infinity and negative infinity, the function is never going to go back down below where it is at x equals minus a half. And so I can justify this. I'm going to write my sentence now. I'm going to say, therefore, f has an absolute minimum at x equals minus 1/2 because, and now if I said because f prime changes sign from negative to positive, that would be a good answer for a local minimum, but it's not enough for an absolute minimum. To justify this as an absolute minimum, I have to say because f prime is negative for all x less than minus 1/2, and f prime is positive for all x greater than minus 1/2. And now I've proven that this value at minus 1/2 right here is an absolute minimum. The function doesn't have any absolute maximums, as we can see, because it's going up to infinity on both sides of minus 1/2. As x approaches positive infinity, f at x is going to approach infinity, and as f approaches negative infinity, f is going to approach infinity. So I've only got that one extrema. I'm not asked in the question, if you notice, the question says find the locations of the extrema. It doesn't ask for the extrema themselves, and so I don't have to evaluate at minus 1/2. But if I was asked to find the exact values of the extrema, I could put a minus 1/2 into f at x and I could get that. The last thing to do here is sketch a graph of the function. So I'm going to put my axes here. And the only really important spot on this entire graph is at minus 1/2. And I can see that what's going on here is this function hits a minimum value. It's going to be negative. I don't know what it is exactly, but it doesn't really matter. It's going to be negative there. That's going to be my minimum. I also know that the function is going to go through the origin. That's easily calculated from the original function. I know that I have a vertical tangent here at the origin, so it's going straight up there. And so from this, I can draw the rest of the function. Vertical tangent there, going out like that. And this must be my original expression, y equals 6x to the 1/3 plus 3x to the 4/3. Of course, anytime I draw a graph, I should be putting arrows on the ends of the axes. And I should be labeling the axes. And that's all I need in order to answer that question. So local extrema, we're looking at a labeled sign chart most times. Absolute extrema, if we're on a closed interval, we can sometimes get away with a candidate test, and sometimes we need a labeled sign chart for that also.